There's a handy little technique that sometimes we'll utilize when we have a limit, and in that limit we have an absolute value. So that's what we're going to look at here. First of all, how can we evaluate these limits with absolute values, and without using a table or something like that. The technique is really what it is. It's rewriting the absolute value without absolute value bars. So let's just think about the most basic absolute value function, I guess you might say. The absolute value of x. Okay, absolute value of x, fairly easy computation, right, when you plug in the x there. However, if I wanted to write that function without absolute value bars, turns out I can do that, and I can do that with a piecewise function. Two pieces, define a function into two pieces, and that's going to be the same thing as the absolute value. Now here's how it works. Obviously, if I plug in some values of x, they come right back out, don't they? If I plug in 5 for x, what's the answer? 5. If I plug in 6, I get 6. So sometimes the x that you plug in just comes out to be x. All right, so we'll say that's our first piece here. Maybe backwards order, but I think it makes sense. Now, what values can I do that with? Well, I can do that with 0, 1, 2, 3, anything above 0. Because if I plug in a negative number, I don't get a negative number out, right? So anytime I plug in a positive number or 0, I get x right back out. So that's if x is greater than 0. Or, I mean, we can put the equal to part there, it really, as you'll see, won't matter, but you see what I'm saying? If x is a 0 or a positive number, then x comes right back out. So that's what we're saying. If it's an absolute value and it's greater than 0, it's really just x. However, if x is a negative number, less than 0, what happens? Well, if I plug in -2, so my x is -2, what do I get? Positive 2. Well, how is positive 2 related to -2? It's the opposite of -2. Right? It's that. Isn't it? Without the absolute value? Because it's positive 2. So if that's the x, then if absolute value, if we're less than 0, it's minus x. It's minus the x. Because that's going to make, if x is negative, that'll make a negative negative, that'll make it a positive. Okay? So that's how this is going to work for those absolute values. Now, that's the most basic one. What if we have something else? Well, it's similar. What if I had the absolute value of x minus 3? Well, it's going to work very much the same. I'm going to that part of it's going to be x minus 3, and then guess what the other part is? Minus of x minus 3. Okay, so it's similar to that, except now we've got x minus 3, so we've got to do x minus 3 minus of x minus 3, okay? Now the other part to this is, where does that break up? It's not at 0. I guess the easiest way to see it is, let's go back to this one and look at the graph. If I graph y equals absolute value of x, what shape do I get? V shape? Yeah, you get the V shape. And where does the V happen? Well, it happens at x equals 0. When I graph this one, any thoughts? What does that one look like? Also a V shape, but if you know anything about the shifting, minus 3 on the inside here, that's going to make it shift to 3 units to the right, 3 units to the right. So the V happens at 3. So guess where I break up the absolute value here, the piecewise, at 3, yeah. It's wherever the V happens, whether it's 3, -3, 5. So if x is, it's x minus 3, if x is greater, sorry, if x is greater than 3, greater than or equal to, you put the equal to, it doesn't matter, you put the equal to part on either one. Now, the only other little tricky business here that that can happen is this. What if, I'm trying to think of what I just want to do here. What if I had, yeah, let's do this. What if I wanted to do the same thing, but with x cubed, the absolute value of x cubed? Well, let's just look at the graph here, first of all. Because you can, I mean, with our graphing calculators, graph just about anything. On the TIs, absolute value is under the math menu. So if you go to math on the TIs, if you have Casio, it's a little different, but it's under math, and then arrow over to the num screen, and ABS is right at the top. So it looks like ABS, for absolute value would be ABS. ABS of x cubed. Okay. You might have to zoom in a little bit to see a corner. Let's see. Yeah, you might see a corner in this one, but maybe this wasn't my best example. Tell you what, let's do x cubed minus x cubed minus 1. I think, just to make it a little more clear. Yeah. Make it x cubed minus 1. Because then you can clearly see where my corner is. So I want it. Okay. So it's going to be x cubed minus 1 and then minus of x cubed minus 1. Now, the only catch is, well, which piece is which? Is this one the x is greater than 1, or is this? Because it's not maybe as obvious as you might think. This one is not always the greater than 1, and this one the minus one the less than. It could be, but let me just explain it this way. The piece that gets the minus is the one that's flipped up. If we just did, so this is y equals the absolute value of x cubed minus 1. Okay, if I graph y equals x cubed minus 1 without the absolute values, here's what it looks like. And so what I'm seeing is, when I go from this to this piece here is down here. And so that's what I'm saying. This piece for this graph gets flipped up. Right? This piece is just this piece of this one flipped up above the x-axis, flipped over the x-axis, let me say. that way. That's the piece that gets negated. So in other words, this will be the minus, and this will just be the regular x cubed minus 1. So it is, in this case, maybe I should have done it different, but you see what I'm saying? And the equal to part doesn't matter. We'll do another one, I'll show you. All right? But that's what we're going to do to, when we have limits, we're going to get rid of the absolute value bars by either doing x or minus x. Okay? All right. With that in mind, let's talk about it. All right, so if it's a limit, as x approaches 1, and we are going to go from the left, and it's going to be absolute value of x minus 1 divided by x minus 1. Okay, so how we evaluate that is, I say, let's try to get rid of the absolute value bars. And the way we're going to get rid of the absolute value bars is just what we were just talking about. For absolute value of x minus 1, I can either go with the x minus 1 or the minus of x minus 1. And so the decision is, which one do I use here? Well, if it's x minus 1, if x is less than 1, I mean, these are, sorry, but if x is greater than 1, I've done them backwards here. They're probably an equal to part, doesn't matter. But, and so, yeah, which one of those am I going to use here? If this is the x greater than 1 part and this is the x less than 1 part, which one am I looking at in this particular case? Well, I want to go to 1 from the left. 1 from the left, is that the greater than side of 1 or the less than side of 1? Well, 1 from the left is, I'm approaching 1 on the x from the left. That's the less than side of 1, right? So I'm going to use the minus of the x minus 1. So I'm going to rewrite this limit. And I'm going to replace the absolute value by the minus of x minus 1. Because, now what can I do? Well, without that absolute value now in place, I can look at some canceling, can't I? The x minus 1's cancel here. And so all I'll wind up with is the limit as x approaches 1 from the left, but all I've got, it's negative 1 over positive 1, so it's essentially just negative 1. And so as x goes to 1, what does negative 1 go to? That'd be negative 1. Yeah? Okay? Okay, what about the limit as x approaches negative 3 in the right, and then it's going to be x squared minus 9 over the absolute value of x plus 3. Well, the decision is, do I want to make absolute value of x plus 3 be just x plus 3, or is it minus of x plus 3? That's our decision here. Well, I'm approaching negative 3 from the right, and this is, this is if x is greater than negative 3, and this is if x is less than negative 3, and equal to part doesn't matter here. But since I'm approaching negative 3 from the right, which one of these would I use? I'd use this one, wouldn't I? Because if I'm approaching -3 from the right side, that's from the greater than side of -3. So I'd want to just go with the x plus 3, you see, instead of the minus. And so in that case, we just do, on the bottom, we just do x plus 3. Now, unlike the previous problem, that's so I can just come down here. Unlike the previous problem, I still have a little bit of work. I need to factor that top, and I guess I could have done it on that step too, but it's a difference of squares. And so it's x minus 3 times x plus 3 if I factor it. Aha! So now I can cancel the x plus 3, as we've seen we can do. And so now, unlike before, I can do some substituting, can't I? The x goes to -3, so I can just, since those are out of the way, the answer is -3 minus 3, -6. So that gives you a way, way of doing this. Now, another way they may phrase a question here, so for the same function, does the limit as x approaches -3 of x squared minus 9 over x absolute value of x plus 3 exists? Well, the reason we like this question is because this harkens back to our original thoughts on limit. For a limit to exist, the limit from the right has to equal the limit from the left, doesn't it? The two limits from both sides have to be the same. We've got here the limit as -3, as x approaches -3 from the right. So we have to look at both sides. So we also have to think, well, what is the limit? So we got to look at both sides. And in this case, since we started that with that problem over there, we've got the limit from the right. We just need to look at the limit from the left. So what is the limit as x approaches -3 from the left of x squared minus 9 over the absolute value of x plus 3? Well, that's from the left, and so that would be from the less-than side. I erased it, but on the less-than side, I'm talking about the minus, aren't I? So this would be the limit as x approaches -3 from the left. Be x minus 3, go ahead and factor that top. But since I'm approaching -3 from the left, I'm going to replace my absolute value by the negative of x plus 3. Negative parentheses x plus 3. What's that change? Well, it changes the fact I cancel the x plus 3 still out, but what is that? Yeah, then I can plug in the -3. But what do I have on the bottom? A -1. So it is -6, but it's divided by -1, which is +6. What does that tell me? That the limit from the left is 6. The limit from the right, though, is -6. The limit from the right doesn't equal the limit from the left, does it? So the limit as x approaches -3 does not exist. And like I said, the nice way of writing it is the limit from the left doesn't equal the limit from the right. It's negative 3 in it. If they wanted to explain it. Okay? Make sense? One other one I better talk about is this one. Is that okay on that one? Okay. Limit as x approaches negative 2 from the right of 5x plus 10 over the absolute value of 8 plus 2x minus x squared. What is that? Limit as x approaches negative 2 from the right of 5x plus 10 over 8 plus 2x minus x squared, the absolute value of that. Okay. When it gets, these absolute values get a little more complicated, you may not necessarily want to write out what that function is. You may not need to write it out anyway, but what I'm saying is I don't necessarily have to write, because it's a little complicated when this stuff gets complicated, so I may not want to write that whole thing out. What I might want to do is just look at the graph here. So let's graph y equals the absolute value of 8 plus 2x minus x squared and see what we can glean from that. All right, so now it's ABS of 8 plus 2x minus x squared. Kind of a W shape, isn't it? Here's what I'm seeing. Well, guess what? We're right at one of the corners there at negative 2. So I'm looking at negative 2 from the right. So coming from this side. All right, well, still the question is, do I want to replace that by 8 plus 2x minus x squared, or do I want to replace it by negative 8 plus 2x minus x squared? All right, so that's why I talked about a little earlier there. Let's look at just the graph without the absolute value and see how this compares. So just take out that absolute value there, and we got this. And so comparing the two then, the parts that get flipped over are this piece to make that, and then this piece. That gets flipped over the x-axis. So what does that tell me with regards to this? Well, if I'm in this range, then I would want the negative of that. You see what I'm saying? I'd want the negative of that. And then if I'm out in this range, I think that's 4. If I'm in the range of greater than 4, I'd want the negative of that. But in here, this piece is not getting flipped over. And so that, I don't want the negative of my absolute value. You with me there? So in this particular case, since I'm approaching negative 2 from the right, so I'm approaching here, what do I want to replace that by? A long way to go, but the moral to the story is, what do I want to replace? Let's look at 5x plus 10 alone for just now. I want to replace, I don't need to negate it because I'm not in this range or this range. I'm coming in at from here. I just want to do 8 plus 2x minus x. If I was approaching negative 2 from the left, then I'd want the negative of that. Does that make sense? 12. Okay. So it turned out it was really nice. All I had to do was get rid of the absolute values there. But it could be, I need that negative there. I just have to decide. All right, well, without the absolute values, now it's just a matter of factoring. And so that, because if I plug in negative 2, of course, I get 0 over 0. Factor off the 5 here. So again, 5 times x plus 2. You can rearrange or factor it just like it is, whatever you want. 8, so we do 4 and 2, I believe. And then minus x squared, so one of them is minus x and one of them is positive x. I think that works, doesn't it? Because that and that will make it 4x minus 2x, which that gives me a 2x. Well, look at that. Voila. X plus 2, 2 plus x, that's still the same. So we wind up with 5 over 4 minus x, so now I can plug in the negative 2. Over 6. So, bit of a complicated problem, but not too bad. Any questions on that? All right. One other type of function besides the absolute value here I wanted to cover is it's called the greatest integer function. Greatest integer function. The greatest integer function, maybe you've seen it before, but the way the book denotes it here, there's different notations for it. The way this book will denote it is these little double square bracket things. That's the greatest integer function. Here's what the definition is. The greatest integer of x is the largest integer that is less than or equal to x. Largest integer that is less than or equal to x. So let's just compute a couple of these greatest integers just to get a feel for it. Okay, so if it's the greatest integer of 4.1. Greatest integer of 4.1. So my x is 4.1, so I want the largest integer that is less than or equal to x. All right, so thinking about the integers, 4 would be an integer, 3 is an integer, 5 is an integer. But I need an integer that's less than that, and I want the largest one that's less than that. It's going to be 4, isn't it? Easy enough. Now, what if I get closer over there to 5? Is that 5? No. Because I need the largest integer that is less than or equal to x. 5, even though 5 is closer integer, it has to be less than or equal to x. So the answer there is still 4. For ones that are greater than 0, it's basically you're just chopping off the decimal part, right? That's what it's 7.239. 7, that's what I'm saying, you just chop it off. Or, I mean, if you're doing fractions, say 5/4, well, you want to look at the decimal, of course. It's 1.25, so that would be 1. All right, now it gets a little tricky. You got to be careful on the negative side. If you want the greatest integer of negative 2.3, the answer is not negative 2. Why not? Think about the number line here. Here's negative 2, here's negative 3. Negative 2.3 is somewhere in between that. So why is it not negative 2? Well, negative 2 is on the greater than side of negative 2.3. So for negative 2.3, the greatest integer is negative 3 because that's the one that's less than. You can't go greater than your number. You want less than. So that's negative 3. So that's what's that. The negatives, they're a little trickier there. You got to go. I mean, it's still the same thing, but it's not just chopping off the decimal in that case. With me? Now, if you're on an integer, well, that's real easy because it's the largest integer less than or equal to x, and so the greatest integer, negative 4, is negative 4. So if you're on an integer, if you're doing the greatest integer of an integer, it's just the integer. So that's pretty sweet. Pretty nice. All right. Let's talk the graph. Because that can be helpful to kind of picture this out. So what does it look like? The greatest integer of x. 1, 2, 3, 4. Well, I think if we do a few, I think we can see the pattern here. Let's just think table here. Okay, so we're at 0, greatest integer is 0, 0.1, the greatest integer of that would be 0, 0.2, the greatest integer is 0. So yeah, 0.9 is 0. So we're hanging out at 0 for the y value until we get where? Well, at 1 it's going to take the jump, isn't it? At 1 would be at 1. So we've got 0, 0, 0.10, 0.20, 0.50, 0.90. So we're hanging out at 0, so we're cutting across to 0 until we get to 1, where at 1 it jumps to 1 in the y value. So we go all the way up to 1 there, a little open circle, and then jump up and put the dot, if you will, up at 1, 1. Okay? Now guess what happens from 1 to 2? Well, 1.1, you got 1 for the greatest integer. 1.2, you got the greatest integer is 1, right? So it's going to hang out at 1 for y until you get to 2. Then at 2, it's going to take a jump to 2. And then hang out 2 to 3 at 2. And then take a jump to 3. So I think you can see the pattern. Stair steps, isn't it? The pattern continues back here. So between 0 and negative 1, or negative 1 to 0, we are at negative 1. Yeah, at negative 1, you're at negative 1, negative 0.3, negative 0.3, you're at negative 1 as you go down to the lower integer. Yeah, so these steps continue. Negative 1 to negative 2, or negative 2 to negative 1, it's at negative 2. And then between negative 3 and negative 2, it's at negative 3. Okay. So that continues. You ever seen that before? Never seen that before? Okay. All right. Well, so they might then ask, okay, so I guess you have to graph it to see, but what if we threw a limit in there? Let's say we do the limit as x approaches, let's approach negative 2 from the left. the greatest integer of x plus 4. There's not a nice little technique of getting rid of the integer bar, greatest integer bars. I would just suggest, let's look at a table. See if we can find pretty good evidence there. Just use a table like we did before. So I want to approach -2 from the left. Here's -2 on the number line. So I want to approach -2 from left. So what values, if I did a table, would I be looking at? -2.1. -2.01, -2.001. Those would be on the left side of -2. Maybe there. All right. So if I plug in those, I get the greatest integer of -2.1 plus 4.